Hello, my name is Moses Hajai. You remember that we presented a solution for this problem that you are seeing on the screen, but we have received a question from one of you now saying that now firstly it was really good to see how the exam question. Now let me just be clear here. This is not an exam question, it's a practice question. So it is a practice question, not an exam question. So just take note of that. However, you have slightly confused me. The student made reference to the calculation of thermal resistance. He said that in the HNNC food process operation book, thermal resistance is calculated by distance it travels divided by thermal conductivity multiplied by area. Page 87 of that book. That's an example too. Now, in my tutorial, he said, however, your tutorial states that you calculate thermal resistance by distance it travels divided by thermal conductivity, and then after summing all the thermal resistance, you bring in the area. Now, these two methods, however, give different results. Now, let me just be clear here. What I did in my tutorial is what the student said here. Yes, I divided the distance it travels, which is S, by thermal conductivity. So that's what I did. But the student said that these two methods, however, give different results. I guess this means different results. So I copied the email directly here. So it means different results. My question therefore is, which is the correct method? The one detailed in the HNC book or the one explained in the tutorial? Now let me be clear here. Both of them are correct and they will give you the same result, not different results. Now I'm going to demonstrate that in this video. What I'm going to do first is to have a quick revision of what I did earlier on the computation of the heat transfer through the heat transfer through the wall of the core store. So I'm going to do a recap of what I did in the previous video. Now, this is the question. This is what we are given. We are given a core store with a height of 3 meters, the length is 10 meters, another the breadth here is 10 meters, and we are also given the thermal conductivity of the construction materials. So I drew this to show us the materials, looking at the configuration of the materials inside the wall. We have the brick, insulation, aluminium. We have the outer boundary layer. We have the inner boundary layer. Then this is the ambient temperature, the temperature outside, which is 10 degrees Celsius. And then inside the cold store, we have minus 25 degrees Celsius. So that's what we have. Then we have the thickness of each of the materials. Here we have a 0.1 meter for brick, 0.1 meter for insulation, 0.006 meter for aluminium. So that's what we have. Then we have the outer boundary layer, because we've been given the outside surface heat transfer coefficient. So that is why outer boundary layer is very, very important. So we also have the inner boundary layer, and then we have the coefficient to be 3. So what I did in the previous video, I'm going to repeat that. So the formula that I used in the previous video is Q equals A dt divided by summation RT. Now, where our RT is the summation of thermal resistance. This is what is causing problem for the students. Now, let me just be clear here that if you use this method or the approach in the HNNC, you're going to have the same result. Now, I'm going to demonstrate here, like I said. Now, for the one that I did, you have your R naught, for example, is 1 over H naught. You see, area is not here. Area is not going to be put here. So it is I over 1 over H naught. So I want us to understand something. If you want to calculate the thermal resistance for the brick and you include area in that calculation, in that computation, now the question I want to ask, if you are calculating the thermal resistance for the outer boundary layer, are you not going to include the area? So it's important that you also include the area here. If you're going to include the area in all of this, in RB, RA, R naught, area must also be included here so as to have the same unit. I'm going to demonstrate that to you now. To calculate the thermal resistance, it's best to do it by using 1 over H naught for this, and for RB you use X over K. That is the approach that I use, which is straightforward I believe. So that's the approach that I use. Now for our R naught, you have our 1 over H naught, which is going to be 1 over 5. Now, and the area, the final answer that we have for thermal resistance for the outer boundary layer is 0.2 meter square Kelvin per watt. Then for inner boundary layer, we do the same thing for the brick. Now, because this is solid, somebody can say, yeah, it's very easy to calculate the area of solid, and you can easily put A here, yeah, which is going to be understandable. But in order to avoid that problem with the fluid, the outer boundary layer and the inner boundary layer, that's why I excluded area in my computation of thermal resistance, and which I believe is the best approach to do. If you look at some other textbook like R. Smith, you will discover that the approach used in R. Smith is what I used in the previous video, and the same approach is what I'm explaining on now. So you calculate your thermal resistance without area. That's the approach used in R. Smith. So you have S over KB for brick, then you have your final answer. You do the same thing for insulation, you do the same thing for aluminium, you have your final answer. Then you sum them together, then you have your thermal resistance to be meter square Kelvin per watt. Now what I want you to understand is, if you compute your thermal resistance by including area in the denominator, you will discover that this meter square would disappear. So you'll be having different units if you include the area. So just take note of that. So you have this as a thermal resistance. Then, because we need to find out our area, now remember that E is going to be transferred through the walls. We have 1 at the other end, 2 here, 3 at the other end, 4. We have 4 different walls. Then you have 4 walls. Then we have the floor and we have the roof. Now your area will not be summation of all of them. Surface area will not be summation of all of them. So your area is very important. So to calculate your area, you will need to, don't forget that our temperature difference is not a problem. 10 minus 25, which is 35, that's not a problem. Now for walls, area for wall, for one of them is 3 times 10, 30 meters square. Now for roof or for floor, because they have the same dimensions, 10 by 10 for roof and for floor. So we have 10 times 10, we have 100 meters square. Now this is the formula that I use. Now you can see that A is included in this formula because A is not in this formula. So what we need to do now is to bring them together. We want to calculate the Q for walls. The Q for wall will be 4 times the area of the wall multiplied by the temperature difference divided by a summation of thermal resistance. You do the same thing for the floor, you do the same thing for the roof. Then because I have this temperature difference and thermal resistance, because they are constant, so I bring them out. Area for wall and area for roof are not the same, so you can't bring them out, you can't factor them out. So I bring this one out, then I have this one inside the formula. Then all I need to do now is just to put in the value. Delta T is 35. This is what we've calculated before, our summation of thermal resistance, not including the area. So we have this again for the area. Then final answer, we have our Q to be 3,536.92 watts, which can be which is approximately 3,537 watts. That is what we have for Q, using my approach, which I believe is correct. Now let's go and use the approach in the HNC book. Now same problem but different approach. Now if you want to use the approach in the HNC book, now we want to bring in A into the thermal resistance. We want to bring in A into the thermal resistance. So if you divide the numerator by A, that's the area, and the denominator by A, because if you do something to the numerator, you need to do it to the denominator. You divide this by A in order to cancel out this A, and in order to bring in A into this formula. What we need to do is to divide. Don't make the mistake of multiply. Yes, division is, if you divide, I'm gonna show you something now. if you divide it, this A is going to be coming in as a denominator to RT. Now this A will cancel out this A. So you have what you're going to have is, I call this RTA. This is the same thing as thermal resistance, but this thermal resistance is including the area. So which is the approach they use in HNC. Now we have the theta T up. Now we now need to find out our area, because what you have done now is you've already included the area and the thermal resistance. So the very first thing you need to do is to find out the area, and the area is not just for the walls, it's not just for the roof, it's not just for the floor, is the summation for walls, floor and the roof, because the question says we should find out the rate at which it will penetrate the coastal, include all walls, floor and roof. So you need to calculate all the area for walls, for floor and for the roofs. So a wall is 4 times area for one wall, then plus the area of the floor plus the area of the roof. So we have 4, which is because we have 4 walls. Then for one is 3 times 10. Then for floor is 10 times 10, and for roof is also 10 times 10. So we have this as the area. Now we've been able to establish our area to be 320 meters square. That's our area, meters square. Now we want to find out our R naught. Now our R naught will now be 1/5 times area. Don't forget that this RTA that we have here has been, we are now using A. Take note of the unit. The unit now is Kelvin per watt. Is no longer meter square, because area is coming in, and you can see the area coming in. This area here, meter square, we cancel meter square, because this is minus, this is plus, they will cancel out each other. So you have your Kelvin going up, then this is going to be denominator, so we have this. Do the same thing for your R high, then you have this. Then for your SB, now we are bringing in area. Now you do the same thing for insulation, you do the same thing for aluminium. Yeah, then summing them together, you will have this. Now this is what you have. You take note of the unit. The thermal resistance here, because it has taken in area with it in the computation, so meter square has disappeared from here. So this is what we have as the summation for the thermal resistance. So we've been able to find the thermal resistance that includes area in its computation. So then we know that our outside temperature and is 10. We can find out what that will be. We know that is 35. That is simple and straightforward. So our dt will now be 35. Now you discover that A is missing here. A is no longer here because we've already used A in the computation of our thermal resistance. So by the time you divide this by this, you will get this, which is the same thing. Which is the same thing as what we have before. This is this Q that we have. You discover that you'll be having the same value for Q. So thank you, and if you have any question, please do not hesitate to get in touch with us, and I hope you enjoy it. For reference, please, you can still use this, and you are free to get in touch with us for any additional clarification. Many thanks. Bye.